terms a little bit, because we've had some discussion this week about exactly what do we mean by quiescent galaxies, quenched galaxies, early type galaxies, as in the title here. So in this talk, I'm going to be talking about early type galaxies from the ATLAS 3D survey. So this is a survey, a complete volume limited survey of early type galaxies in the very local universe. So they're selected in K-band to have a magnitude brighter than this, which means a stellar mass greater than about 10 to the 9.3. They're all within 42 megaparsecs, so it's a complete volume limited survey of all of these galaxies that are visually classified as early type, so both S0 and E, that are observable by the WHT. And this leads to a sample of 260 classified for morphology early type galaxies. So, it's been known for some years that there is some cold gas around early type galaxies and in early type galaxies. We heard about gas around them earlier today in those very nice talks. Today I'm going to be talking about the gas in them. So first off, H1, the atomic gas that sits inside galaxies. It turns out quite a lot of them have it. 40% of early type galaxies that sit in field environments have H1 gas. And it can be quite a lot of H1 gas. These are H1 masses from 10 to the 7 to 10 to the 10 solar masses of gas sitting in and around these galaxies. Here are some examples of interferometry from the Vesterbroek telescope. You can see these very nice big disks that sit around the central early type galaxy. You see more disturbed things sometimes, like these, but the majority of the H1 is in large disks and rings that sit around the galaxies that are more or less dynamically relaxed. So you say, well, this is a lot of gas. Why are these things not spirals? Well, it turns out that the column densities, as we heard earlier in the week actually, are a little bit lower on average than the spiral galaxies. So here the blue line is the typical column density of H1 in spiral galaxies, and here in red is our early type galaxy sample from ATLAS 3D, from this paper by Paulo Cerda, and you can see that they're typically, the typical column density of H1 around early type galaxies is an order of magnitude-ish below the typical column density of H1 in spiral galaxies. So it's quite low column density and it sits there and it forms stars at a very low rate, if at all, in its outer parts.
But is that statement still true at roughly the same galactocentric distances? Because a lot of that very high column density gas sits in a very central region of the spiral galaxy, not necessarily in the outskirts.
So this is, yeah, so the stuff that's here probably is in the centers, but we also include the galaxy centers here. And you can see that you don't reach quite as high. So they both include the whole radial range. So this gas probably isn't forming stars and influencing the galaxies that much, but it does provide a reservoir. So, can you get gas that really alters your galaxies? And the answer is yes. So we did a complete sample of all of these volume limited early type galaxy sample. We detect molecular gas, so CO, in 1 in 4 to 1 in 5 galaxies. 22% of early type galaxies in the local universe have cold molecular gas. This can be 10 to the 7 to 10 to the 9 solar masses, so that's as much as the Milky Way in the center of some of these galaxies. The molecular gas fractions, however, as these are much more massive galaxies, range from 10% down to a very small fraction of a percent. Typical is 1% or a little bit less. We only detect molecular gas in fast rotating early type galaxies. It doesn't seem to matter whether they're E or S0, that classification doesn't really matter here. What matters is whether or not they're really slow rotators. Those 10% of galaxies in the universe that don't seem to have molecular gas, and that fits with the picture of how we think they form through dry merging. Whereas the fast rotators, they have fast rotation, they've had dissipative pasts, and those are the ones where we can detect molecular gas. The detection rate for molecular gas is independent of both the luminosity of the galaxy itself and its environment. So you detect just as much molecular gas in early type galaxies in the Virgo cluster as you do in the field. The molecular gas is also relaxed, dynamically cold, and is often in disks and rings. So this is interferometry from our thesis. You can see these nice ring-type structures, effects of bars, misaligned disks, but it's kinematically relaxed in 90% of cases. So this is not train wreck galaxies. They're regular and relaxed.
Can I ask about the H1? Is most of the H1 also in fast rotators?
The H1 is also found in some slow rotators, but I can't remember the numbers exactly off the top of my head.
Yes.
But yes, it is found around slow rotators too.
But the incidence is higher amongst fast rotators.
I would say that, but I should check the paper for the exact number.
It's my memory.
Yeah, that's right.
Okay.
This is the peril of using someone else's laptop. Thanks, Greg.
That's because that changed.
Thank you. So one thing I just wanted to mention, these detections, they don't avoid the red sequence. So these are the Atlas 3D galaxies, the crosses here. The red dots are our CO detections. The size of the dot gives you the mass of H2 sitting in these galaxies. It's a morphologically selected sample, so we don't avoid these early type galaxies that sit in the blue cloud, and we detect more of them. That's great. That makes sense. They're forming stars. They're blue. But even here at the very tip of the red sequence, you can have galaxies of 10 to the 9 solar masses of molecular gas sat right in their centers forming stars, as I'll show later, merrily, and still they sit in the red sequence. So we want to answer a few big questions in this talk. So are these galaxies being regenerated or being quenched? We talked a little bit about that on Monday. Where is the gas coming from? And is it forming stars? And if so, is it forming stars in the normal way? A little aside as well, are these objects quiescent? Depends how you define it, of course. They have molecular gas and they have star formation, so some people would say no, but they are in the red sequence. This is the specific star formation rate plots that everyone seems very keen on these days. Star formation rate versus stellar mass. This is the star formation rate main sequence up here. And you can see 80% of our galaxies lie more than 10 times below the main sequence. So if you want to use that as your classification for quiescent objects, you're still going to detect a sizable fraction of early type galaxies with cold molecular gas. And a similar fraction would also be selected if you do a passive color wedge.
Just ask a quick question. How do you measure the star formation rate?
So here, I'll go into this in a bit later in the talk, but this is WISE and GALAX. So I'm going to go through and try and answer these three questions in my remaining time. Firstly, are these galaxies regenerated or quenched?
Or neither.
Or no? So the evidence that I'm going to use here is the following. These galaxies are essentially indistinguishable apart from in the fact they have gas and therefore maybe in some cases slightly younger stellar populations arising from this gas from the other early type galaxies on our survey. They have the same bulge to total ratio, same environment, same masses. So it doesn't seem like there are special populations that's just transiting. They're identical to the others other than the fact that they happen to have cold gas. And here I show evidence that their color distribution is completely consistent with galaxies on the red sequence that have acquired some gas somehow, have a burst of star formation, and then have conveyed back onto the red sequence again. So here, if you take galaxies on the ridgeline of the main sequence, this red line here at t equals 0, and you drop in a typical amount of molecular gas, 10 to the 8. That's what we find, is the typical amount of molecular gas. You set up a burst of star formation. You come straight down to this red line here in the U minus R color, and then with time you step back up here until you're back on the red sequence. You end up slightly redder because you've got higher metallicity. So the question then is, this covers all our points, the locus of points, very nicely. So that all of these galaxies could be being regenerated from an event and then fading back onto the red sequence again. And that means that the mechanism that's supposed to have kept them quiescent in the red sequence may have failed. There's also, of course, some of these galaxies could be fading up from the blue cloud, but statistically they're all consistent with regenerated galaxies.
If you drop 10 to the 8 solar masses in a big disk, is it going to really form stars that rapidly and bring you down to the blue cloud?
So these...
That's not much gas.
So this is assuming they fall in disks of a typical size of the disks we observe. so affecting the colours within 1RE, which is where we're measuring them in the data as well. So we're trying to match everything to our observed data in this plot.
So before you said that they don't depend on the luminosity, I would say there is a dependence on luminosity there.
Well, so what I mean is the detection rate. I mean, this is a slightly different color plot, but if you look here, statistically, I mean, if you measure how many galaxies we have here in the early type galaxy population as a ratio to the number of galaxies that are detected, it's the same.
Strength of the amount that you have.
Well, but this is a complete volume limited sample, right? So we have everything that exists in a whole volume.
So this diagram is hugely misleading because you're plotting the entire galaxy population here as opposed to the early type population. The massive galaxies that when you put your up arrow, those are the galaxies that live in that space are all massive disks. So they can't just be early types that have like a little bit of star formation and fade. You'd have to get rid of that massive disk at the same time.
Yes, I agree with you completely. I mean, this arrow, the position of it is not meant to signify anything in particular. It's just a cartoon.
Its direction is also the same.
It
I mean,
is.
it's supposed to be
Yeah.
No, more massive is this
fade.
one. Well,
They don't get brighter. As
yeah,
they-
maybe you don't get brighter.
As star formation
You'll
fades,
get more
you
massive.
dimmer.
If you merge, you'll get more massive.
Yes, but you get fainter.
You get
Or
faint.
what?
These are cartoon arrows. Please don't read much into their
No,
direction.
this is
All right, let's.
This is a cartoon plot. So these are my
So
conclusions.
this
That
number
one?
of 40%, that's within some mass range.
That is the complete mass range of early type galaxies that exist. So it's greater than 10 to the 9.3 in solar masses to everything that exists within that 42 megaparsec volume. So our most massive galaxy is M87. So where is the gas coming from? If you want to regenerate galaxies, there's two main places you can get gas from. You can either get it from the stars, losing mass, back into the ISM. If this gas can cool, you can regenerate perhaps your molecular gas reservoir. Alternatively, you can accrete from an external object. You can have a merger, or H1 clouds can fall in, for instance. And what we can do to find out which one of these is happening, one of the ways is you look at the molecular gas kinematics, or any of the gas phases in fact, because they're all coupled. The internal stellar mass loss should rotate like the stars that formed it. It has to conserve more or less the angular momentum that it came off with. The external gas to first order can rotate in any sense it likes, because it's coming in from an external source unrelated to your host galaxy. So we can use our sample to see what's dominant. What we find is that if you plot, this is a histogram of the angles between the gas. So here we have two examples. Stellar velocity field, gas velocity field, this one's aligned. The angle here between this angle and this is 0. Here you have a ring that's completely counter-rotating. So that would be 180. If you look at this histogram, you'll see two-thirds of the galaxies have aligned gas, and 1/3 have misaligned gas. But there's also a strong environmental dependence there. In the clusters, galaxies are essentially all consistent with being aligned. And in the field, you have 50% of your galaxies with misaligned gas.
Is there also a mass dependence in this?
Yes, so the most massive galaxies are always aligned. I'll show this in the 2011
They're
paper.
probably also all in clusters.
Yeah.
Sorry?
They're probably also all in rich environments.
No, so that I do the plot in the paper. There is a separable environment and mass effect. So certainly there are more massive galaxies in clusters, but the most massive fast rotators are not all in clusters.
But the mass loss comes from mostly it's a BB star, so it's a stellar population which is like 5 billion years old or something. So if we actually had a major merger that has very different rotation senses, then we must still have a fraction of the stars, original ones, going in different bands to the average kinematics. And then you'll actually get mass loss which will not respond to the total stellar kinematics.
Yes, so it depends on the mass fraction of that merger, whether we would see that in the stellar kinematic maps. If it's formed a large proportion of the stellar population, and those stars are of course going to be brighter because they're younger.
Not the large portion, maybe half.
Well, if it was half, we would see it. So, because it's luminosity weighted, our measurements of the stellar kinematics.
But it's all mixed up, so if the
It's
cup goes
mixed-
one
it's
way,
mixed
cup
up
goes
for
the
sure,
other way, on average
but you
don't
can
go-
separate off them, separate kinematic components, and you would at least see a lower dispersion, a higher dispersion.
Do you include the brightest group galaxies in this at M87, or are they not in this?
So M87, all of the galaxies we detect are fast rotators, and M87 is a slow rotator, so it's not here. There are central group galaxies here, yes, but we don't have any massive groups within this volume, so that there's not really the most extreme galaxies, the things with cooling flows and things in our sample, because we don't probe that sort of volume. We also see other evidence for gas accretion. So for instance, this is a metallicity map of the stars in the center of one of these molecular gas hosting objects. The gas sits in this area, and you can see lower metallicity seen where this gas is, so suggesting the stars are formed from low metallicity gas. Thank you. Dust to gas ratios are also lower, again suggesting minor mergers are the source of this gas. However, you can also look at this theoretically. This is a paper that Claudia Lavis and I put out this year, and actually, if you look in the semi-analytic models, you can quite well predict the H1 and the H2 mass functions found in these galaxies. So here we have the H1 mass function with the semi-analytic models as the curves, and you can see they go quite well through the data. And this is the mass fraction, so how much H1 you expect in each galaxy. And once again, you can reproduce pretty nicely the shape of this. The same with the CO ones. So with the H2, as long as you have a sensible round pressure stripping scheme in your SAM, you can do a very good job of reproducing the H2 mass fraction and mass function. But in the semi-analytic models, most of this gas comes from cooling from the hot halo. If this is true, then you require the hot halos to have some angular momentum. It doesn't have to be massive, but it has to be some. And it requires these hot halos to be misaligned from the galaxies, at least 50% of the time in the field. Or you have to have more gas-rich minor mergers than are currently predicted in the semi-analytic models. So is this sensible? Well, what we've been doing now is implementing a new semi-analytic treatment following the spin flips of the halos. And you can actually get a very good fit if you do this by tracking the change in the dark matter angular momentum and assuming that the gas follows that. So this is our observed histogram in the blue here. And this is the first try with the SAMs reproducing this, and we do reasonably well. And you also project the correct mass dependence, so this is the mass dependence plot someone asked about. Our most massive galaxies are almost all aligned, apart from this one, which is a group center. And the colours here are the contours from the SAM, and you can see they match pretty nicely indeed. Observationally, we can test whether this is going to be really the case once ASTRO-H comes online. It's a new X-ray satellite that will have the spectral resolution to see if hot halos rotate directly in the X-ray lines, which would be very interesting indeed. So, here's my conclusions about this. There's accretion that dominates in the field, but also perhaps there's cooling. So as my final point, is the gas forming stars? And if so, is it forming stars normally? The answer, is it forming stars, is yes. So here we measure a star formation rate from a combination of Galax and the 22 micron WISE luminosity. It's the same as the 24 micron Spitzer, more or less. And measure the star formation rates using standard calibrations against our gas density. So this is a classic Kenneker-Schmidt type plot. So they are forming stars. And if you just look at the axis here, see typical, you're forming 0.1 to 1 solar masses a year, maybe slightly lower on average around here, which is actually more stars per unit area being formed in the center of these early type galaxies than in typical spiral disks, which are the black points here. So they are forming stars and reasonably vigorously, because they have quite high gas densities sat in the center of these objects. But the star formation efficiency of these galaxies is low. It's low by a factor of 2.5. I can't see what number that is, but I'll assume it's low. Thank you.
Are the objects that are below Kenneker-Schmidt also the same objects which are in the wrong, where you would say that quenching is succeeding?
No, so these are just the galaxies with gas. The galaxies without gas.
But you showed the distribution of galaxies with gas in the color diagram, right? And I'm saying there's some galaxies for which you're saying the quenching mechanism is working, there's some others where you're saying it's failed. So shouldn't the ones that are below Kenneker-Schmidt also be the ones where quenching has failed?
No, I said
quenching
that
is working,
all,
sorry.
all of the galaxies that are detected, there must have been some sort of failure in keeping them quenched, because they now have gas. The 40% figure is the number of early type galaxies, the fraction of early type galaxies in the local universe with gas, not the fraction with gas that are quenched.
And all your H masses all come from zero, right?
Yes, so we have an assumption.
What are you using?
We have an assumption about XCO here. We take the galactic value because these are high metallicity systems. Of course, if that's wrong, then these move, but we don't think you can move them in a sensible way to get rid of this. There's an analysis of that in the
So
paper.
what is metallicity? They're probably super slow.
Yeah, supersolar. So in fact, they would move even higher on this axis. So you would have more gas.
Not that super solar.
Not that supersolar though. So and
Like
that
what?
correlation is fairly flat.
So
So
it's like 1.5 or 2? Or what?
they can go up to 3, but only in the most extreme ones.
But they're typical ones, not a lot like.
More like 1 to 2.
But that's not necessarily the metallicity of the gas, if it is a minor.
Exactly.
Right.
Exactly.
No.
So there's sizable uncertainties there, but we don't think you can systematically change all of them to get them back on the Kennecke-Schmidt law. Interestingly, this depletion time difference correlates with the shape of the potential of the galaxy. So here I show that if most of the gas is in the center, in the rising part of the galaxy rotation curve, you get quenching, you get longer depletion times here. If the gas is very extended, so it goes further out into the galaxy, then you get normal star formation in these galaxies. This also correlates with the shear in the central regions. So the torque as these clouds are rotating around. Perhaps these clouds are being pulled apart. There seems to be a dynamical effect at work here that's suppressing it. In this study I presented here is not of resolved galaxies, but we have the data to do that, and that's where we can really test whether this is a dynamical effect ongoing or whether this is just a coincidence. So, my big questions are up there, so I'll go on to my conclusion slide. 22% of early type galaxies have molecular gas. 40% of them have H1 in the field. That means in the field, nearly 50% of early type galaxies have some cold gas. So some of this quenching is not working, or maybe we just don't need it to stop this gas being there. We just need it to stop forming stars in the right way. So I'll leave the rest up and take any questions. Thank you.
Mike, can you come up, please? We can only take 2 questions, and I saw 2 hands, so that's it.
Really quick.
Rachel.
So your Kennecke plot was for total gas. If you make just an H2 based plot, are they still a factor of 2.5 lower?
Yes, it essentially
So it's
doesn't
not the
change
ratio
because the
of-
H1 in the inner regions is not much by mass.
Ratio, this is represents its H too. H1 they would be.
Yeah, the H1 is very low.
Or non-existent.
Yeah.
Sugata.
So in galaxies where you have misaligned gas, you also see tidal density when you do your deep CFHT.
Yes, so to get at least the fact we have this M-Atlas project where we get deep CFHT imaging with MegaCam to look for very faint tidal structures around the galaxies. We have a program to try and get all the CO objects that are misaligned versus the aligned ones to look at that. We're still waiting for data to come in to confirm, but it does look like there are tidal structures around many of the misaligned galaxies, so that does seem to be a coincidence, but I don't want to give you statistics until we have them.
All right, we're going to have to cut off the discussion there. Thank you again, Kim.